This unit, we're going to talk about some aspects of linear algebra, specifically helping us solve a system of equations, of linear equations, using matrices. So first, let's define some terms. A linear equation is an equation of the form a sub 1, x sub 1, plus a sub 2, x sub 2, etc., all the way up to a sub n, x sub n equals b. Now the a's are all constants, and b is also a constant. And then the x's, x sub 1, x sub 2, all the way up to x sub n, those are the variables. This is stuff you're familiar with, but the notation might be a little different, so that's why it's important to make sure you're familiar with this type of notation. A solution to the linear equation, discussed above, is going to be a set of values for each of the x variables. So x sub 1 is equal to a constant, we'll call it c sub 1, and x sub 2 is equal to another constant, c sub 2, etc. Now some of these constants may be the same, they could all be different, it doesn't matter, they're just real numbers. The set of all the solutions to a linear equation is called the solution set. So one particular solution are specific values we plug in for the variables to make the equation true. All those possible solutions make up what's called the solution set. So for example, what if I asked you to find one solution to this equation? Now, if you know anything about graphing in 3 dimensions, you'll realize that this could represent a plane. And we know there's an infinite number of points on a plane. So there should be an infinite number of solutions to this. I'm just asking you to find one. So how can we find one? Well, we can just start picking values for your variables. So, I don't know, let's say, for example, I let x sub 1 equal 3. And then I'll let x sub 2, let's see, that'd be 6. How about if I let x sub 2 equal negative 1? So right now that's going to give me 6 plus 1 plus 4x sub 3 is equal to 11. So I subtract. So that's going to make x sub 3 now, I can't just pick a value, it has to be a set value, and that's going to be positive 1. So one solution, and if you write this as an ordered triple, we could either write it this way, specifying what each variable equals, or you could write it as an ordered triple. And so that would be one solution. Not that that's any better than any of the other solutions. So for example, 0, negative 7, 1 would also be a solution. Okay? But now, the next part of this is the interesting part. What if I ask you to find the solution set? So I want you to find all the solutions. Well, obviously you can't just list all the ordered triples, because that goes on forever. So we need to generalize. And so what we do in this situation is we'll say let, and pick one of the variables. I'll pick x sub 1. Let's let that equal some value s, which represents a real number. And then I'm also going to let x sub 2 equal t, another value. Once I have these two values set, the third variable, x sub 3, now I don't have a choice, just like in the example when I picked specific numbers. So now, if x sub 1 is equal to s, and x sub 2 is equal to t, then what would x sub 3 have to be? Then that would be 11 minus 2s plus t divided by 4. So I could represent the solution set for this equation as s comma t comma 11 minus 2s plus t. Now you'll find in a linear algebra class, a professor might specifically say, I want you to assign s to this variable or t to this variable, or maybe even use other letters. So we could have done this a little differently. What if, on the other hand, I said, oh, you know what? I'm going to let x sub 1 equal s, and I want to let x sub 3 equal t. Why would I want to do that? Well, if you look at the equation, The x sub 2 has a coefficient of 1, so that'll be a little easier to solve for. So in that case, then x sub 2 is going to equal what? 2s plus 4t minus 11. So we could represent the solution set for this linear equation as s comma 2s plus 4t minus 11 comma t. So that would be acceptable as well. So you can see there's different ways we can represent these. So now for either of these, if you pick a value for s and t and plug it in, you will get an ordered triple that satisfies that equation. Okay, so let's work backwards here. Is 9, negative 4, and 2 a solution to this system? You might want to hit pause, test it first, and then when you think you have your answer, go ahead and press play again. Well, if we tried in the first equation, 9 for x, negative 4 for y, 2 for z, that does equal 3. So it seems pretty good. Let's try it in the second equation. 2 times 9 is 18, minus 4 is 14, plus 2 is 16. Check. Looking good. Let's try the last equation. 9 minus 4 is 5, plus 4 is 9, not 7. So that one doesn't work. So it has to work in every equation to be a solution for the system. So now we're talking about systems of equations versus one specific equation. So we have 9, negative 4, 2 is not a solution to this system of equations, but it is a solution to the first two linear equations. And that's what we want to focus on, is systems of equations. An m by n, and that's how you read that, the mxn, you say an m by n system of linear equations consists of m linear equations in n unknowns. So in the example above, we would say this is a 3 by 3. Let's pick a different color. We would say that this is a 3 by 3 system because there's 3 equations and there's 3 unknowns, or 3 variables. A solution is a set of values which satisfy all the equations simultaneously. Okay, so let's start off simple, baby steps. Solve the system of equations. Now, you've learned how to do this way back in probably later on, second semester of Algebra 1, so a long, long time ago. So how would you solve this system? What ways are you familiar with? Well, you probably think graphing, although it's not in y equal mx plus b form, so using a graphing calculator or graphing software wouldn't be so easy. You might think substitution, and if you could solve one of the equations for a variable and substitute that into the other equation for that variable, you could solve it. Or probably most of you would do elimination. And that's where you add the two equations together, or you add a multiple of one equation to the other. And so either way you want to handle this, let's say I'll do a system. If I multiplied the first equation by 2 and added that to the second equation, then I'd wind up with 7x, and then the y's would cancel out, equals negative 14, so I'm going to get x equals negative 2. So x equals negative 2, and then I can plug that back in to figure out what y is. So if x is negative 2, probably plug it into the first equation, although it doesn't matter. And then I'm going to get negative 4, I add it to the other side, I get y equal 1. Now the nice thing about solving systems is it's really easy to check, and if you make a simple arithmetic mistake, you'll find it when you check. So negative 6 minus 2 is negative 8, negative 4 plus 1 is negative 3, it checks out. Okay, and we get one solution. Now we know these are two lines, and they're not parallel, and they're not the same line, so they intersect at one point, so we should get only one solution, and that's it. So we have some terminology for the different cases of your solutions. So if an m by n system of linear equations is consistent, we call it consistent if it has at least one solution. So the example above would be consistent. It's inconsistent if it has no solution. And then two other terms. We say that a system is underspecified if it has more unknowns, i.e. variables, than equations. So if there's more variables than equations. So for example, if I had two equations and each equation had 3 variables, that would be underspecified. It helps, I think, when we're talking about systems to think visually, at least with smaller systems. So if I have 3 variables, that's a plane in 3 space. If I have 2 equations in 3 variables, that means I have 2 planes. And what are the possibilities? Well, they could be the same plane, we'd get infinite solutions. They could be parallel planes, we'd get no solution. They could intersect, and their intersection would be a line, so that's also infinite solutions. When we talk about vectors in 3D, we'll get more into that. And then if there's more equations than unknowns, we would say it's overspecified. You could think even more simply, just how about if we had 3 equations of 2 variables each? So that would be like drawing 3 lines in a plane, or on the Cartesian coordinate plane. And so with those 3 lines, chances are they probably are not all going to intersect at one point. And if 2 of them are parallel, there's going to be no solution. If they all intersect at a point, we'll get a point for a solution. If all 3 happen to be the same line, we get infinite solutions. So it's good, I think, to have a geometric perspective as we deal with this. Okay, so that ends part 1, and then you can go on to part 2.